Outflows looking at his watch, so we tried to actually start on time. Unlike almost everything else in the world, we'll actually be on time. We apologize for the seating. It's a little unusual this week. We'll be back to our regular seating, but this is the way we found it set up. We'll try to get it back to the usual setup for next week. This is better? Yes. Okay, well, we can vote. You can send in your emails to Outflows, and you can vote how you want the seating set up. Anyway, I'd like to welcome you all. This is our third Stephen Murray Distinguished Lecturer series, and the speaker today is going to be Alison Coil. She was an undergraduate at Princeton. She did actually spend 1 year here at CFA, so she's a regular. She knows how everything is done here, and she's sort of coming back home. She did her PhD at Berkeley after her visit here. She mostly worked on Deep 2 there. I think that was the beginning of her survey years. She's now an associate. She had a Hubble Fellowship, and she's also at the University of Arizona. She was now an associate professor at the Center for Astrophysics and Space Science at UC San Diego. Her work, when you look at all of her papers, is like an alphabet soup of Deep 2, Aegis, Primus, and now MOSDEP. Her interest focuses on large-scale structure, surveys of all wavelengths, galaxy AGN clustering, and galaxy and AGN evolution. Her talk for this now third Stephen Murray Distinguished Lecture will be AGN host galaxies, fueling, and feedback to redshifts of 2. And I'll give you Alison.
Thank you. Well, thank you very much for inviting me. I'm here for the whole week. And yeah, I've spent time here. It's been 18 or 19 years since I was a regular here. But a lot of people are in the same offices. But it's really fun to come back. I really, really enjoy being here. So my schedule is still fairly open. I have some openings tomorrow, but a lot on Friday. So especially after this talk, if anybody wants to come talk to me, particularly grad students and postdocs, do sign up. There's a Google Calendar. Okay, so I'm going to be talking about AGN host galaxies, fueling, and feedback at both intermediate and high redshift. My collaborators on this work are primarily James Aird, who was a postdoc with me at San Diego, who's now in Cambridge working with Andy Fabian, and then several of my graduate students, so Mojigan Azadi, Jane Leung, and then a previous student of mine, Alex Mendez, who's now a postdoc at Johns Hopkins. And for the second part of the talk, I'll be talking about an ongoing survey called MOSDEP. These are the co-PIs of that survey. Okay, so I'm really interested in the role of AGN in galaxy evolution. There's a lot of hints that AGN probably are very, very important or critical for understanding how galaxies grow with time. So a big question is whether and how AGN regulate galaxy growth. So one of the motivations for this is the M-sigma relationship, that basically as galaxies are getting more massive, their black holes are getting more massive. And some people are saying that this relationship means there has to be some sort of feedback from the AGN to the galaxy to regulate its growth. There's also this idea that AGN feedback is responsible for determining the shape of the high mass end of the stellar mass function. So the blue line here is the stellar mass function for galaxies, and then the dashed red line is the halo mass function for dark matter halos. They don't agree. So this is where star formation is most efficient, where baryons are getting turned into stars, and then the efficiency is lower at both lower masses and high masses. The general idea is that at lower masses, this is due to stellar feedback, and at higher masses, this is due to AGN feedback. That's the general idea. So the details of this are not at all clear. And it's not even really clear to me if this is entirely due to AGN feedback. So there's a lot that we need to still understand here. But it does seem like AGN are probably very important for understanding the growth of galaxies and the shape of the stellar mass function. Also, for simulations to match the observed galaxy properties, basically people have to have AGN feedback be pretty strong and quench star formation. So the way that you make a galaxy red and dead and not forming stars anymore, you have to heat and or remove the gas in the galaxy. And the only process so far that seems really viable for most galaxies is AGN, some sort of pretty extreme form of AGN feedback. So all of these questions are somehow related to AGN feedback, but the details of this are very unclear. Okay, so some key open questions are, first of all, just which galaxies even have AGN to begin with? Is there something about a galaxy that determines the likelihood of it hosting an AGN? And then, do the AGN that we see commonly drive outflows, and what are the physical properties of those AGN-driven outflows? It's really important to understand the details of this to understand the impact that those outflows could have on their galaxies. It's not just enough to see that there are outflows. You need to know what that's actually doing to the gas in the galaxy. So this is the real question, is what impact does AGN feedback have on host galaxies? And then a related question is, do AGN regulate star formation? So another observational piece of evidence that galaxies and AGN are co-evolving is if you look at the star formation rate density, the global star formation rate density in the universe is a function of redshift. So this is 0 out to a redshift of 9. The points here are for star formation rate, and then this line here is scaled up black hole accretion density. So this is from the Xray luminosity function. And they have pretty similar shapes. They definitely both peak around redshift 2. So redshift 2 is the epoch where the galaxies are growing the most, and you have the most black hole accretion happening in terms of cosmic time. And then they're both declining at low redshift, maybe not identically, but the error bars are still sort of large there. So we really want to understand the correlation between galaxy growth and black hole growth, and whether the AGN is impacting star formation, and then also, again, whether it really quenches star formation, because we still don't know how to make ellipticals. So I'm not going to answer all these questions today, but I'm going to start to address several of them using results from 2 spectroscopic redshift surveys. So for the first half of the talk, I'm going to talk about results from the Primus survey, which is at redshifts of around 0.5 to 1. And then the second half, I'll talk about the MOSDEF survey, which is at higher redshifts of around 2. Okay, so first I'm going to start with several different results from the Primus redshift survey. So this was a spectroscopic faint galaxy redshift survey that we did on IMAX on Magellan. This is when I was a postdoc at Arizona with Daniel Eisenstein. Mike Blanton was the other co-PI. So we used a low dispersion prism to measure redshifts to 0.5%. So here are examples of what our spectra look like. And this doing a low dispersion prism allowed us to go very wide and build large samples very quickly. So the survey covers redshift 0 to 1.2 to a depth of I of 23, so fairly deep. And it's just a large sample. So it's 120,000 spectroscopic redshifts total. Most of those are galaxies, covering 9 square degrees on the sky over 7 independent fields with multi-wavelength coverage. And the reason we wanted these different fields was to really beat down cosmic variance, because cosmic variance is still the dominant error bar on most measurements of galaxy and AGN evolution at intermediate at high redshift. Okay, so there's a lot of research being done on AGN host galaxy demographics. So there's a lot of papers looking at whether galaxies that are having their star formation quenched more likely to host an AGN. People were looking for sort of indirect evidence that if there's an AGN there, the galaxy is probably going to have its star formation quenched, or just recently did. There's also a lot of papers looking at whether or not there's correlations between the star formation activity and the AGN activity at the same time in individual galaxies. So the first thing I'm going to show you is using the Primus galaxy sample. So we didn't just go look at AGN. All of this work is embedded within galaxy surveys. So starting with a galaxy sample, we quantified the probability that a galaxy of a given stellar mass and redshift hosts an Xray AGN of a given specific accretion rate, which is the AGN bolometric luminosity divided by the galaxy stellar mass. So it's a proxy roughly for Eddington ratio. Okay, so this is what we found. So here's this probability that a galaxy of a given stellar mass and redshift hosts an AGN as a function of the AGN specific accretion rate or Eddington ratio. And this is 3 different relatively narrow bins in redshift. And again, this is from Primus. And the blue points are for star-forming galaxies, and the red points are for quiescent galaxies. Okay, so the first thing you'll see is just this power law. So there's more low Eddington ratio AGN than high Eddington ratio AGN. This is not what you would just observe. You have to correct for selection effects. If you just look at what you observe, it looks more like this. So to get this power law, you have to correct for various observational biases. But when you do that, you get this power law. It's pretty similar for star-forming and quiescent hosts. The black line here is a fit to all of both galaxy populations together, and you can see that it's increasing. So this normalization is increasing with redshift. So at a given stellar mass, galaxies at high redshift are more likely to host an AGN of a given accretion rate. And then comparing the star-forming galaxies to the quiescent galaxies, there's a difference here. It's about a factor of 3. So a galaxy is about 3 times more likely to host an AGN if that galaxy is actively forming stars. Okay, so that doesn't mean that there are no AGN in quiescent galaxies. There's actually a lot in quiescent galaxies. I feel like with Herschel, people have sort of forgotten about that. But if the galaxy is actively forming stars, it is 3 times more likely to have an AGN. Okay, so that was a really rough split of the galaxy population into just star forming or quiescent. So let's look at this in a little bit more detail, since we do see this difference of a factor of 3. So this is now star formation rate versus stellar mass. The contours are showing you the galaxy population. So here's the star forming main sequence. This is like the blue cloud, and then this is the quiescent red sequence. So now I'm going to take this star forming population and just split it into 2 populations, basically above the main sequence or below the main sequence. So this just means that a given stellar mass, it's either a highly star forming galaxy or not as star forming galaxy. And then we're going to do the same thing with the quiescent population, just split it into high or low star formation rate at a given stellar mass. And when people look at this plot for galaxies, sometimes the thought is that galaxies up here maybe have higher gas fractions. That's why they have higher star formation rates. Maybe there's more merger activity. And maybe less down here. And then the idea within the quiescent population is that these galaxies have more recently had their star formation quenched. So they were forming stars more recently than these galaxies. These are like the really red, dead, old galaxies. Okay, so we're just going to split the galaxy population into these 4 bins and then look again at the likelihood of hosting an AGN. So here again is this probability of hosting an AGN at a given stellar mass and redshift, but now split to these 4 different populations. So this is sort of messy. So what I'm going to do is just on the right-hand side here is just plot the normalization for these 4 different populations. So this is just this normalization as a function of specific star formation rate, which is star formation rate divided by stellar mass. Okay, so here's the star forming population. And then the lighter gray points here is if we split it even more finely. So basically within the star forming population, there's no dependence on star formation rate or specific star formation rate. A galaxy, if it's star forming, has the same probability of hosting an AGN, whether it has a high star formation rate or a low star formation rate, which is not what I thought we would see. I thought we would see an increase here. So this is basically saying you're not getting more AGN if you're not more likely to have an AGN if maybe there's a merger or a higher gas fraction. So within the errors anyway, there's no dependence here. But then there's a really sharp decline here. So these are the quiescent galaxies that had their star formation quenched more recently. These are the quiescent galaxies that had their star formation quenched earlier. So again, it's not like there's no AGN, but there's a lot fewer here than here or here. So I think this is really constraining for models of AGN fueling and understanding which galaxies host AGN.
Sorry, Alison.
Yeah.
What's your definition of AGN for this work?
So this is Xray AGN. I'm not talking about quasars.
Okay.
I'm never talking about quasars in this whole talk because I'm talking about host galaxies, and we can't really see the host galaxies for quasars. So these are moderate luminosity. So in X-rays, this is like 10 to the 42 to 10 to the 44. Yeah. Okay, so the other thing I wanted to say was, the gas properties are pretty different for star-forming and quiescent galaxies. You have a lot of cold gas here and you have hot gas here. And yet, within the errors, you see this is basically the Eddington ratio distribution function. And within the errors, it's the same slope for these 2 completely different kinds of galaxies. So I think this points to fueling being a very stochastic process. That if you have more cold gas around, you're going to form stars, and more of that cold gas is going to get down to the AGN. But it seems to be a very stochastic process, and a similar kind of stochasticity is happening, for the AGN in the quiescent galaxies, where maybe it's being fueled more by hot gas, but you have the same kind of Eddington ratio distribution function. So I think both of these plots are very constraining for theoretical models of AGN fueling. Okay, so you have to compare to a complete galaxy sample at a given stellar mass to get this right. There are papers in the literature that are coming to the wrong conclusions because they're not comparing to a stellar mass matched galaxy sample when they say which kinds of galaxies host AGN. If you just go and pick all your AGN and then say, let's look at the galaxies, you're going to find that the AGN that you see are in massive galaxies. But it's not true that a more massive galaxy is more likely to host an AGN. It's just that you're more likely to see it. Because a more massive galaxy has a more massive black hole. And for a more massive black hole, you're always flux limited in your observation. So whether you're looking at X-ray AGN or infrared AGN or optical AGN or even radio AGN, It's always flux limited survey. And so basically in a more massive galaxy that has a more massive black hole, you can see those black holes to lower Eddington ratios. And in the lower mass galaxies, they have smaller black holes and you can only see the high Eddington ratio ones. So there's always this really strong stellar mass observational effect that you need to take that into account when you interpret the host properties. Okay, so what this is showing, this is the same kind of plot, but this is specific star formation rate versus stellar mass. So here's the star forming sequence, here's the quiescent sequence. And again, the contours are the galaxies and then the crosses are the Xray AGN and Primus. So you'll see that on the whole, the Xray AGN are in more massive hosts, and that's for that reason I just explained. But if you just draw lines for where the star forming main sequence is, and the green valleys are galaxies that have had their star formation recently quenched, and then the older ones, you would say, oh, most AGN hosts are below the main sequence. So there's a lot of papers that have done this, have just made this left-hand plot, and basically said, it looks like there's a correlation between star formation quenching and AGN prevalence. And that's not the right interpretation, because at these masses where you can see these AGN, most galaxies are below the main sequence. At low redshift anyway, massive galaxies are quenched. And that's not true at high redshift. But so the right-hand plot is just a histogram of specific star formation rate for the AGN in red and then the galaxies in black for everything above a stellar mass of 10 to the 10.5. And so galaxies tend to be quiescent at these masses. So you can't just go look at the hosts of the AGN and say, here's what kind of galaxies host AGN. There's a really strong observational bias here. And I'm really hammering this point because this has been missed in the literature, and there are still papers that are basically just making the left plot and not coming to the right interpretation. Okay, so I want to briefly touch on this question of whether there's a correlation between star formation activity and AGN activity in individual galaxies. So instead of now going from the galaxy population saying which have AGN, now let's just look at the AGN and look at the star formation rates in the galaxies. So I don't have a plot of this, but there's not a significant correlation in Primus between the star formation rate of a galaxy and the observed X-ray luminosity, which is basically the instantaneous AGN luminosity. It's just a scatter plot. There are papers in the literature that claim correlations between these things, but generally what they're doing there is because AGN are rare, to get a large sample, they use a deep field and then they take all the AGN that they have, which is over a really wide redshift range. And when you do that, you'll see a correlation, and what's happening is that up here, these are all high redshift objects, and here, these are all low redshift objects. So it's just an observational selection bias. So when you do this in finer redshift bins, that goes away. Okay, so there's not a significant correlation between star formation rate and instantaneous AGN luminosity when you're looking at the star formation rate of the whole galaxy. If you flip those axes, though, so now this is the X-ray luminosity of the AGN and then the star formation rate of the host galaxy. The points here are the Primus points. I mean, it looks like a scatter plot, but if you take, there is actually a weak but statistically significant correlation here. So if you take bins and star formation rate, that's what the blue points are, and then plot the median X-ray luminosity and do the correlation coefficient, there's a weak, it's weak, okay? There's a weak, but there is a statistically significant correlation between basically the median AGN luminosity and star formation rate. So the reason that you get a correlation this way and you don't the other way is because here you're taking the median in AGN luminosity, which basically means you're effectively averaging over AGN variability. So when you do that, there is this weak but significant correlation. So what I showed you before was that within the star-forming population of galaxies, if a galaxy has a higher star formation rate, it's not more likely to host an AGN. But what I'm showing you here is that for the ones that do have AGN, if the galaxy, this is just for the star-forming galaxies, if the galaxy has a higher star formation rate, it has a slightly more active AGN. So there's some sort of hint here between the star formation rate and the AGN luminosity, but it's not like a really strong correlation. Okay, so I think the general picture is, again, if you just have more cold gas to fuel star formation, some of that's going to make its way down to the AGN in some sort of stochastic way. And this explains the rough similarity of the star formation and AGN accretion histories that we see in the universe. But again, I just want to point out there are still a lot of AGN in quiescent galaxies. There's just been a lot of Herschel papers that have just been looking at star-forming galaxies, and they seem to kind of forget that there's also quiescent galaxies, and they have a lot of AGN as well. Okay. So getting back to this point of AGN selection biases, all AGN selection techniques have observational biases. And you need to understand these at whatever wavelength you're looking at, because they can differ by different wavelengths. But it's really important when you interpret your results. The good news, especially since this is a high energy seminar, is that X-rays are the least biased. So if I have to find AGN at some wavelength, I want to do it at X-rays. Okay, so this is, again, from Primus. The black line is the galaxy population, and then the colored lines are histograms for AGN selected different wavelengths. So these are just histograms. Left is stellar mass, right is specific star formation rate. And the green is X-ray AGN, the red is radio AGN, and the blue is infrared selected AGN. So like I was saying before, all of these have this strong bias towards identifying AGN in high mass galaxies, because the more massive galaxy has a bigger black hole, and you can see it to a lower Eddington ratio for a flux limited sample. There are some differences here, though. Radio AGN tend to have higher stellar mass than X-ray. Infrared tend to have lower stellar mass than X-ray, and I'll get back to that point in a second. Then there's definitely differences in terms of the star formation rates as well. So X-ray AGN, you basically span the full range. It's not biased in terms of the star formation rate. The radio AGN you only find in lower star formation rate galaxies, and the infrared in higher star formation rate galaxies. So it's just really important to remember this when you're interpreting your data. So I want to say just a couple more things about X-ray versus infrared AGN selection, because there's basically claims in the literature that infrared AGN selection identifies this large population of very obscured AGN that you can't see in X-rays that are maybe Compton thick. And that turns out that that's not true. So this is a plot, don't worry too much about this, but this is basically showing the Venn diagram of the overlap between the X-ray in green and then the infrared in blue or red as a function of the X-ray depth and the infrared depth of your sample. And when you have very deep X-ray data, 90% of your infrared AGN are actually X-ray detected. It was the papers that were claiming that there's this huge population of infrared AGN that aren't detecting X-rays. That was when they had shallow X-ray data. So when you have deep X-ray data, 90% of them are detected. So it's not this like totally new population. But that does mean that 10% are not detected. So that 10% is an upper limit on the fraction that could be heavily obscured Compton thick sources. So it's true that infrared selection will find some additional AGN that are not identified in X-rays, especially if your X-ray data isn't crazy deep. It's definitely useful to also have infrared selection and combine them to get a more complete AGN sample. One more point on X-ray versus infrared AGN selection and the kinds of AGN that they identify. So to identify an infrared AGN, this is the SED of a galaxy in red, and then going up to the purple is you're adding more and more light from an AGN. So basically you need to, at IRAC wavelengths, so near to mid-infrared, the AGN needs to outshine the host galaxy. So what that means is that infrared AGN selection is going to be biased towards identifying luminous AGN and or AGN in not so luminous galaxies. And lower luminosity galaxies at these wavelengths, this basically corresponds to stellar mass. So that means lower stellar mass, which at least at low redshift means star-forming galaxies. So there's this funky selection here which is biasing you both in terms of the kinds of AGN that you're seeing and in what kinds of galaxies you can see them. And again, X-rays doesn't have that bias, just the stellar mass bias. So this is showing just the observed distribution in specific accretion rate, again, basically related to Eddington ratio. So the green is the X-ray AGN, and then the blue is the infrared using this Donnelly selection technique. And you can see that they're not the same, right? That the infrared AGN have higher specific accretion rate, and X-rays gets you down to lower specific accretion rate AGN. So it's a more representative sample to use X-ray selection than infrared selection. I'm not saying that infrared selection is not useful. I just want to clarify that it's pretty biased. Okay, So again, not only are the kinds of AGN that you can identify different, but their host galaxies differ as well. And one way that this is going to be important is in interpreting clustering. So this is a 2-point correlation function. I'm only going to have 2 plots on clustering, I promise. But this is the red is Xray AGN, and the red is radio AGN, the green is Xray AGN, and then the blue is infrared AGN. And there's differences in their clustering properties. This is coming from Primus, but this has been seen in other surveys. Ryan Hickok saw this in booties. Lots of people have been seeing this in the deep fields, that there's these systematic differences in the clustering of AGN depending on their wavelength. And I used to be one of the people that would write papers saying, oh, this is really interesting. Maybe this means something's different about their fueling processes, or there's some sort of evolutionary sequence here. And actually, what we found in Primus, because we have these galaxy samples to compare to, is that all of the difference that you see in the clustering is just due to differences in their host galaxies. So just to go back here. So radio AGN are in more massive galaxies with lower star formation rate. Galaxy clustering depends on both stellar mass and star formation rate. Higher stellar mass is more clustered, lower star formation rate is more clustered within the galaxy population. And basically there's no difference. What this plot is showing is there is no difference between the clustering of AGN and inactive galaxies with the same stellar mass and star formation rate distribution as your AGN hosts. So all of the differences that people were seeing in the literature, it's all just due to differences in their host properties. Unfortunately, that means I don't think we're going to be able to use AGN clustering to constrain anything about AGN fueling. Okay, so those were all results from the Primus survey. Now I want to talk about the MOSDEF survey. So this is an ongoing survey at Keck covering redshifts around 1.5 to 3.5 using this new MOSFIRE instrument, which is a near-infrared multi-slit spectrograph. So this is a 4-year survey. We have 48 nights guaranteed on Keck, which is a fair amount of Keck time. Started 3 years ago, so we're in our last year of taking data right now. The full sample is going to have over 1,300 galaxies in AGN. And the idea here is not just to get redshifts, like in Primus. The idea here is to obtain the full suite of rest frame optical emission lines at redshifts 2 to 3 that people commonly study at redshift 0 in Sloan. So we do multiple filters. So this is redshift 2. We do JH and K filters because we want to get the O2, O3, H beta, N2, H alpha, and S2 lines. So again, the lines that are really commonly used at low redshift. So we're targeting portions of the very deep candles fields that have the deep HST near infrared imaging, and it's H-band selected, so we're not doing alignment break or BZK or something selected. It's basically akin to stellar mass selection. Pretty deep, goes to 24.5 at H-band. So our sample spans a very wide range of stellar mass and star formation rate, and it spans a wider range in these parameters than other surveys at these redshifts. Okay, so in addition to X-ray and infrared and radio AGN selection, there's also optical. Again, I'm not talking about quasars, so I'm talking about Seyferts. So in Sloan, or at low redshift, for a long time, people have used this BPT diagram to identify AGN. So this is the ratio of O3 to H beta and N2 to H alpha. And this is showing you Sloan points here, and you can see these 2 different plumes. So these are star-forming galaxies. These are AGN. And then quiescent galaxies that don't have AGN aren't on this plot because they don't have emission lines. So in Sloan, there's these 2 different lines that people have proposed to identify AGN. This line up here comes from, it's a theoretical line that comes from Lisa Cooley's work that basically says the maximal starburst gets you something below this, so anything above this has to be an AGN. You miss a lot of AGN doing that, so Guinevere Kaufman came up with this empirical line right here to separate the star-forming galaxies from the AGN. So the idea is that where a source is on this plot tells you about the photoionizing source of the gas. So down here, the gas is being photoionized by star formation. Up here, it's AGN, and here, there's both. Okay, so this is what's been used at low redshift. This selection also has biases, which I think have not always been appreciated in the literature. So again, there's this stellar mass bias. That you're going to, again, just be more likely to see an AGN in a more massive galaxy. But there's also a bias here in terms of the star formation rate. So if a galaxy has a really high star formation rate, even if it has an AGN, the light from the star formation is basically going to dominate, and it's going to be moved over here. So there could be AGN hidden in this population, depending on the ratio of the star formation rate to the AGN luminosity. Okay, so this is a plot from a paper I published last year showing the BPT diagram at redshift about 2.5. It's not as large as Sloan, obviously, but this was the largest sample that had been published like this at these redshifts to look at AGN, identifying AGN in the optical. So the red points here are Xray and or infrared AGN. So we knew these were AGN before we put a slit on them with Mossfire. And then the blue points are galaxies or things, maybe they could be AGN, but we didn't know that they were from their Xray or infrared properties. And so our first question was just, does the BPT diagram work at redshift 2? And it does. The AGN separate very nicely here. But they separate in terms of this ratio, the N2 to H alpha ratio, not the O3 to H beta ratio. So this is not the key diagnostic here. This is the key. You can almost draw a line in N2 and H alpha and identify the AGN. So a couple points about this. Because to observe these lines, you need near-infrared spectroscopy, very deep near-infrared spectroscopy. And to get a large sample, you need multi-slit. That wasn't possible until very recently. So there were papers in the literature proposing alternative diagnostics at high redshift where you didn't have this. So it was O3 to H beta versus stellar mass or rest frame color. And I showed in this paper that those just don't work as well at high redshift. They're not as complete and they're sort of contaminated. So it's really best if you want to do optical selection, you need to get N2 to H alpha, which we now can. The other thing that you might notice is that the blue galaxies are a little shifted from Sloan. So the contours here are Sloan. And if you draw a line through the median of the blue galaxies, there's a small shift here of about 0.1 dex. So that had been known for a while. It probably has to do with nitrogen being elevated at high redshift. So what that means is you probably can't just use the Kaufman line. If you use the Cooley line to identify AGN, you're going to miss most of your AGN. It'll be very incomplete. But if you use the Kaufman line at high redshift, it might be a little contaminated. So, sorry, that was using data just from the first year, so less than a quarter of the survey. So isn't published yet, but here's the updated plot using data from the first half of the survey. And again, the pink points are things that we knew were AGN before we targeted them. So they're either X-ray or infrared selected AGN or both. And again, like I was saying, you can have AGN down here hiding in your star formation population. It's just that they have really high star formation rates, so that's why they're over here in this plot. So here's the Cooley line, here's the Kaufman line. I realize this is sort of a detail, but I just wanted to mention this. We're using this new line by Melendez. It's another theoretical line where they include AGN photoionization. And the reason we use it is because it's just elevated relative to Kaufman here where we have a lot of galaxies. So it won't be as contaminated as Kaufman, but it will be more complete than Cooley. Okay, so that's what we're using in Mossfire to identify AGN in addition to using their X-ray or infrared properties. So this is just showing distributions of our AGN selected at different wavelengths. So red is infrared, blue is X-ray, and green is optical. This is showing the O3 luminosity of our AGN. The range is fairly similar for all three of these. The infrared are a little brighter, but again, that makes sense given the biases in infrared AGN selection. Their stellar masses are a little different. So the infrared AGN are in lower stellar mass galaxies, which again is very consistent with what we saw at lower redshifts in Primus. Nobody's looked at this at these redshifts before, but we're seeing a very consistent picture with what we found at intermediate redshifts. And then, especially because of this difference in stellar mass, they do probe pretty different Eddington ratios or specific accretion rates. So the infrared AGN have higher specific accretion rate, and then the optical and the X-ray allow you to go to lower accretion rate AGN. Okay, in terms of their host galaxy properties, so again, here's star formation rate versus stellar mass. The contours are the MOSDEF galaxies now at redshift 2.3. Here's the star forming main sequence. Here's where our AGN are. This is kind of complicated because we're color coding by which wavelength we've identified them. But you can see that they're across the entire main sequence. There's not a difference in the star formation rates of the galaxies at that same stellar mass compared to the AGN. Very similar to what we found in Primus. You'll notice that the green points tend to be below the main sequence. So again, there's this bias against finding optical AGN in galaxies that have high star formation rates. So this is all very consistent with what we saw at lower redshift. You can also, at high redshift, galaxy people like to plot galaxies in UVJ space. So this is the rest frame U minus V versus rest frame V minus J. And they like to do this because quiescent galaxies separate up here from star-forming galaxies. And then within the star-forming population, you can separate dusty from non-dusty galaxies. And if you compare AGN to galaxies of the same stellar mass, then, which is what we've done here, you find that the distributions are the same in this space. But you have to do this very carefully to get the stellar mass distribution right. It turns out the dustiness of the galaxy is a really strong correlation of its stellar mass. And so galaxies with a slightly higher stellar mass tend to be up here, and slightly lower stellar mass tend to be down here. So it's easy to get this wrong if you're not doing very careful stellar mass matching. And again, there are papers in the literature that are claiming that more dusty galaxies are more likely to host AGN or have brighter AGN, but I think that's because they're not matching in stellar mass very carefully. Okay, so lastly, I wanted to talk about outflows, AGN outflows. So one of the things that we can do with the MOSDEF data is, just like in Sloan, we can look in the emission lines for additional blue shifted emission from an outflow. So this is showing two different sources here. This is N2, H alpha, O3, and H beta. And first we fit all of our sources with a single emission line for all of these lines where they're physically, the properties are tied together. And then if that's not a good fit, then we allow additional components. So you can have a second kinematic component. So there can be two Gaussians. You can see here, this is the narrow line region, and then here's a blue shifted broader potential outflow component. And of course, sometimes, you can also have broad H alpha and H beta. So we went and found the ones that had the second kinematic component, and these are potential outflows. And the reason that I'm saying potential and not for sure outflows is because they could be mergers, right? If you have two galaxies merging in the spectra, you're going to have two kinematic components with long slit spectra. So here's showing 4 of our MOSDEF AGN. This is 1 arc-second across, and this is our MOSDEF slit for each of these. So if there's just a single bright object, we think that's probably not a merger, should be fine. If there's disturbed morphology, I should say these are the very deep candles H-band images. So if there's a disturbed morphology, that looks like a merger. This one, I don't know, not necessarily a merger. I mean, at redshift 2, it's not like redshift 0 where you have these nice spiral flat disks. Like, it's very clumpy. So this maybe could be an edge on disk. But anyway, if it looks like there might be 2 nuclei, we call that a potential merger, and we remove it from our sample. And this is not to say that mergers you can't have an outflow during a merger event. I mean, according to simulations, you often get outflows during the merger event. But what we wanted to do is we want to try to understand the physical properties of the outflowing gas. And so we basically want to know that this blue shifted broader component is from an outflow and not a merger. So that's why we remove these from our sample. Okay, so in terms of where the AGN-driven outflows are, their host galaxies are, they're just along the main sequence of star formation. So again, this is star formation rate versus stellar mass, showing the MOSDEF galaxies. It's not like they're all above the main sequence or whatever. They're basically, just normal star-forming galaxies at these redshifts. The blue points are the potential mergers. But the stellar masses that we're looking at are not super high. So they're about 10 to the 10 to a few times 10 to the 11. These are not like extremely massive galaxies at these redshifts. Okay, so in terms of how often do we see AGN-driven outflows in these typical star-forming galaxies? So out of our initial sample of 66 AGN, again, this is using the first data from the first half of the survey, 19 of them have this second kinematic component with signal to noise greater than 3 in these lines. So those are potential outflows. But then 7 of those, we thought that by eye, the morphologies looked like they might be mergers. So we're saying that there are 12 of them are outflows. So the detected outflow rate is 18%, which might seem sort of low, except that this is a very strong lower limit on the actual AGN outflow rate because you need both high signal-to-noise spectra to see this. So this is a histogram of just number versus H-alpha signal-to-noise. The blue is all of our AGN spectra, and then the green is the ones where we detect an outflow. So obviously, the detection fraction is much higher for the high signal-to-noise. I mean, if you look at the spectra, you need to see you need to detect at 3 sigma this blue bump. So you need pretty high signal to noise spectra to see that. The other thing that you need is you need that outflow to be fast enough that you would see that bump separated enough that you could detect it. You know, if the outflow is 20 kilometers per second, it's just going to be a little broader at the base here, and we're not going to detect a second kinematic component. So we can only detect, you know, relatively fast and or high signal to noise outflows. So this is a lower limit. This fraction could easily be twice this. Okay, so the first point is AGN-driven outflows are fairly common in AGN in typical star-forming galaxies at redshift 2. And then in terms of their kinematics, so the velocity, these are just 4 more examples. So here's the O3, and here's N2 and H alpha for 2 different sources, where you can see the second kinematic component here. So if you just take the velocity shift between the center of the narrowline region and the outflow region, that velocity shift ranges from around 100 to 500 kilometers per second. So these are not tiny outflows. Those are fairly substantial outflows in terms of their kinematics. But because of orientation effects, generally, at least at low redshift, outflows tend to be biconical. They're not spherically symmetric. And so we're probably not, you know, generally they're not going to be pointed right at you. So you're not seeing the bulk velocity along the line of sight. So if you take the maximum velocity in the outflow that we see, that probably corresponds more closely to the bulk velocity of the gas. And that is a higher number. So it ranges from 300 to 1,300 kilometers per second. So again, these are not wimpy in terms of their kinematics. And then the full width half max ranges from 100 to 1,300 kilometers per second. We can also get outflow sizes. So this is not AO data, this is long slit data, but we do have spatial information in the long slit. So for radio people in the audience, this will make sense. For other people, this might seem a little strange. So this is a 2D Mossfire data. So you've got wavelength on the x-axis and then position along the slit on the y-axis. So here's the H alpha and N2 lines for a single AGN with an outflow. So the bright white area is the narrow line region, and then this right here is the outflow. So it's blue shifted, so it's lower wavelength. And then you can see that it's also spatially offset from the narrow line region. It's not just here, it's up as well. So what we can do is we can integrate all the flux in the 2D spectrum just over the narrow line region and then over the outflow region. So this is flux as a function of position along the slit. For the blue is the narrow line region, and then the red is the outflow region. The green is the continuum. And you can see, this is just the same thing as normalized. You can see a shift in the centroid. We also, on our Mossfire masks, we always observe a star so that we can track what the seeing was for every spectroscopic observation. So we can also compare the width here to the seeing disk and see if it's resolved. So half of our AGN outflows are resolved. And the full width half max of the physical extent is not small. So it ranges from 3 to 10 kiloparsecs. So these are galaxy-wide AGN-driven outflows. And then roughly half, a little more than half, are also spatially offset from the narrow line region with a maximum physical offset of up to 7 kiloparsecs. So these are relatively fast galaxy-wide outflows that are being driven by moderate luminosity AGN. These are not quasars. And again, these are not in really massive and or like sub-millimeter type galaxies. These are in just your regular star-forming galaxies on the main sequence. We have one particularly interesting source that has 2 outflows. So here's N2 and H alpha and O3. So here's the narrow line region. This is kind of hard to see, but basically the white contours here, there's more on the left than on the right. So there's an outflow here that has a velocity offset of 160 kilometers per second, and it's not spatially offset. And then there's this, which is this. It's much easier to see in O3. So the O3 line for the narrow line region, there's a skyline there, which is why we don't see O3 for the narrow line region, but we see it really strongly for this second outflow, which is faster. So it's 340 kilometers per second, and it's offset by 7 kiloparsecs, which is just huge. So we're not totally sure what's going on with this source. I mean, that's definitely real, and that's the O3 and that's the H alpha. So we're confident about the redshift and that it's associated and stuff like that. I don't know, maybe this is evidence for episodic AGN outflows. So we have one crazy source like this out of our 12. You can ask about so what impact are these outflows having on their galaxies? So you can roughly get an estimate of the energy injection rate into the ISM of the host galaxy. So to do this, we're assuming an energy conserving bubble into a uniform medium, which is maybe not the best assumption, but it's what people are doing in the literature. So to compare with others, basically this energy injection rate depends on the physical size of the outflow squared and then times the velocity cubed. And so we get energy injection rates around 10 to the 42 to 10 to the 44 ergs per second. So this is about an order of magnitude lower than the outflows that are seen in ULERGs at redshift 2, both because our sizes and our velocities are a little lower, but they're not that much lower. And this is about an order of magnitude lower than the bolometric AGN luminosities. So the AGN certainly have enough energy to drive these outflows. Okay, so another question is, there's this new idea of positive AGN feedback. So in case people were tired of hearing about AGN feedback too much, now there's a whole nother way. So usually AGN feedback is thought to be negative in that it shuts off star formation. It clears away and or heats gas in a galaxy. But now there's this idea of positive AGN feedback, where an AGN drives a jet, a radio jet, that then shocks the ISM in the galaxy and temporarily induces star formation. And it doesn't last that long, but anyway, so first an AGN will create star formation, and then later it'll shut off star formation is the idea. So first positive and then negative feedback. So here's one example of where this seems to be happening in the universe. So this is at relatively low redshift. Here's an elliptical galaxy. It has radio jets. If you can see the pink here, that's the AGN jets. And then this blue object, this is H alpha emission. There's gas here along the jet that it looks like the jet is, impacting and shocking. And so it uses this high density gas that's cooling and forming stars. Okay, so here's one object where this seems to be happening. So the question is, how widely does this happen? Joe Silk has been interested in this idea for a few years, and one of his collaborators ran a simulation. So this is showing you a galaxy disk from the top where there's this ring of induced star formation. So as this AGN jet appears, it induces star formation in this ring that moves outward. And so they have papers talking about how maybe this could be responsible for inside-out galaxy growth, for example. Okay, so do we see this happen commonly in the universe? So here's the MOSDEF sample. So now we're taking, again, just the AGN. We're taking just the outflow component. So if you took this, and there's spectra along this jet. If you take spectra and take the emission lines and put the gas on this jet on the BPT diagram, the gas here is in the star-forming region of the BPT diagram, telling you that the gas is being photoionized by star formation, telling you that there's star formation at the location of that gas. So we don't see that in MOSDEF. So here's all of the AGN outflows. If we take just the outflow only component and say, where is it in the BPT diagram? Basically, all these lines are different ways of identifying AGN, but they're all up here. They're not down here in the star forming region. Okay, so we're not seeing triggered star formation along these outflows in MOSDEF. This is not a large sample. So then I thought, okay, let me go to Sloan where you have statistics. So on the left-hand plot, again, this is optical. So BPT selected AGN, taking just the outflow component in the spectra and saying, where is the outflowing gas in the BPT diagram? And it's up here in the AGN region. And all of the papers that talk about positive AGN feedback, what you need is you need this radio jet to compress the gas and induce star formation. So I took the subset of these that are radio AGN, and that's plotted over here, and there's no difference. In fact, if anything, they're more likely to be up in the AGN region. So I would say this is pretty clear evidence that positive AGN feedback is not rampant. I don't know, maybe it happens, but it can't last for very long, and it doesn't seem like it's happening that often. Okay, so to conclude, so I have 2 slides with conclusions. So first of all, I just really want to make this point clear that understanding AGN selection biases is really, really important in interpreting your data. So it impacts interpretation of the host galaxy demographics. AGN accretion rate distributions, AGN clustering. And galaxies at a given stellar mass and redshift are 3 times more likely to host an AGN if they're actively forming stars. And there are weak but significant correlations between the time averaged AGN luminosity and star formation rate in individual galaxies. And I would say that we're not seeing strong indications that AGN, again, not quasars, just moderate luminosity AGN, quench star formation by looking at their host galaxy demographics. I think of the early papers that all saw this, they weren't taking into account stellar mass effects. And once you compare it to galaxies of the same stellar mass, all of that goes away. AGN fueling seems to be a pretty stochastic process on small scales. And I'm saying that because we get this same negative power law for both star-forming galaxies and quiescent galaxies in terms of the Eddington ratio distribution. But there is this correlation that the more cold gas there is in a galaxy, if it's forming stars, the more likely it is to host an AGN. So probably the more cold gas you have in a galaxy, more of it is eventually getting down to the AGN to fuel it. And then AGN-driven outflows appear to be fairly common in moderate luminosity AGN at redshift 2 in normal star-forming galaxies. And I'm saying this because prior to this work in the literature, all the results were on either really massive galaxies or submillimeter galaxies or ULERGs. And we're finding that it's actually really common for AGN at redshift 2 to drive these outflows. They're often spatially resolved or offset from the galaxy. So we detect physical scales, the outflows on physical scales of 3 to 10 kiloparsecs. So these are galaxy-wide outflows. In terms of the impact that this is having on the host galaxy, we haven't estimated mass outflow rates yet, and those are very uncertain, so I think it's going to be hard to say for sure. But I would say at a minimum, these AGN-driven outflows need to be impacting the host galaxies at least as much as star formation-driven outflows, which we already know really do regulate star formation and impact morphologies of galaxies. So I do think AGN outflows are important for understanding galaxy evolution. And then finally, positive AGN feedback does not appear to be a widespread phenomenon from an observational point of view. Okay, thank you.
Maybe there can be a little bit of light.
Yeah, can we turn on the lights?
You were mentioning the positive feedback, but I couldn't see what is the spatial extent of the region for which there could be positive feedback in the simulation and also in the Minko's plot.
Yeah, so in the simulations, it happens, so it starts on small scales, but at least this is the only simulation I know of that has done this, but it goes out to scales of around 5 kiloparsecs. So it does propagate out into the disk. I think in this simulation it only lasts for something like 15 million years. So maybe it just doesn't last that long, and maybe that's why we're not seeing it more. I don't know. Oh, so this is the one object where it seems like it's happening, but I think this is something different. That's not in the disk. That's an elliptical. I think there just happened to be some gas nearby there. So I think this is the more interesting question, is whether it's happening in star-forming galaxies. And there's not like a smoking gun object where there's a disk where you can say that this is happening. There's really indirect, but like kind of this evidence that just like doesn't go away. So there might be something there. Especially at high redshift, there tends to be a correlation in the angle of the radio jet and then like elongation in the star formation rate. So if you plot contours of star formation rate and then you plot, so like that's interesting, but that's not like bam, right? Yeah.
Right now?
So, yeah, exactly this picture. So why is it in a ring? Because this jet-induced star formation should be at a specific location.
Yeah.
Why is it in a ring?
Yeah. So again, yeah, I think it's pretty different physically what's happening here. So in this simulation, yeah, they talk about that, but they basically say that while you get these collimated jets on small scales, okay, so unlike here where it's like you have this jet and it just hits the gas and it compresses it, the idea here is more that I think that you're getting a lot of energy out into the disk, and then at least this is at low redshift. I think that actually I can't remember the thickness of this disk, but basically, no, you know what? This is at high redshift, so it's a thicker disk. So as soon as you get energy out, it kind of goes to the the easiest place, right? So basically the energy pretty quickly, it's like the opening angle gets, of not the jet, but of the impact of in the ISM of the host galaxy, it starts to impact the ISM on much larger angles. So they talk about this in their paper. Yeah, I mean, I understand what you're saying, but I do remember reading the paper being like, okay, it seems plausible.
There's all those simulations from jet induced star formation, which go back pretty long, I think, even in the 90s or like this kind of thing. There's always like along the jet.
Yeah.
It's really like localized.
Yeah.
So very different from what
Yes. Yes. Yeah. So I can't remember the first author on this paper, but I think Joe Silk's the second or third. He's the one who's really been pushing this idea. So it would be nice to see more simulations that try this.
Yeah, I'm worried about the contention that only 10% of Xray AGN, the Compton-thick Xray AGNs are only 10% of the population.
Mm-hmm.
And the obvious concern is that that those Compton-thick ones are also not selected by the infrared, which we have some evidence is true. So in the Primus survey, did you do anything, or are you able to do anything with the optical selection? Because you lose
No.
the H-alpha?
No, yeah, because the resolution, the spectroscopic resolution is not high enough. We can't.
Resolution.
Yeah, so N2 and H alpha are completely. Actually, we don't even cover those wavelengths, but everything's too blended. So
Okay.
you need higher resolution to do that. But yeah, there could be an additional population that's not seen in either. But my main point was that when you have really, really deep X-ray data, you do actually detect 90% of the infrared selected AGN. That's the main point.
Scott, would you have?
Oh, I was just going to say something related to Reinald's point. I mean, so if you have two jets that drive shocks, early on the shocks are just, have the tips of the jets, but later on they do become elliptical, sort of, so you would expect to see the string, and in fact you see that in observations of outburst, AGN outburst shocks.
In clusters.
In galaxies and groups, like at
Okay.
NGC 5813 is something we've done a lot of work on. You see 3 elliptical shock edges.
Okay.
And it's the known as 0.7 KV group.
Okay.
So it's plausible.
Yeah.
Before we let everybody go, I have one more question. You talked a lot about the selection effects. When you're comparing the AGN and the star formation, are there any issues with the time scales that you're comparing AGN, which can have relatively short time scales,
Yeah.
and turning on and off with the star formation, which can have appreciable longer time scales?
Yeah,
Is
for
that-
sure.
that an issue?
Yeah, no, definitely. So that's why if you just plot star formation rate versus X-ray or AGN luminosity, it's just a scatter plot. And there's no significant correlation. But if you would instead basically time average your AGN luminosity by, not really time average, you're just averaging over a bunch of AGN. So they're at different evolutionary stages. They're flickering at different levels. So once you do that, then you start to see a correlation. So yeah, I think part of that lack of observed correlation is due to variability. The other thing, there's a paper by Alex Diamond Stanek at lower redshift that looks at the global star formation rate in a galaxy and then the AGN activity and shows that there's no correlation. But if you look at the nuclear star formation rate and the AGN activity, there is more of a correlation. So it might also be, there might be a couple things. One is that AGN flicker. The other is that the global star formation rate might not be that tied to the nuclear star formation rate. But, when people are talking about AGN quenching star formation, you do want to be looking at the global star formation rate.
No more questions? Let's thank Alison one more time.
Thanks.